we're looking at here is 2 glasses of blackcurrant squash. They've both got the same volume of liquid in them, but this one is clearly more concentrated than this one. You can see just by the colour. This one is darker and this one is a paler colour. And what that means in terms of osmosis is that this one has more water molecules available, and if we were to put a partially permeable membrane between them, the water would move from the dilute solution to the concentrated solution, which is pretty much what you will have learnt at GCSE. But it can be a bit confusing because we're talking about the movement of water, and yet this isn't concentrated with water, it's concentrated with blackcurrant squash. And this one has more water molecules. So then you end up tying yourself in slightly verbal knots, saying that it's the movement of water from an area with a higher concentration of water to a lower concentration of water. So a much better and more scientific way to think about it is by thinking in terms of water potential. So if we want to think about water potential instead of just thinking about dilute and concentrated solution, we of course need to know what it means. And the definition of water potential that I'm writing here is that it's a measure of the potential energy of the water molecules and their tendency to move from place to place. So that's the definition of water potential. And it's really affected by solute molecules. So my squash that I'd added to my glasses was affecting the water potential in those glasses because solute molecules form weak bonds with the water molecules. So if normally we had water molecules, this is a very scientific diagram, but if we normally had water molecules that look like that, that's my glass of squash, and I add in some solute molecules, what happens is they form weak bonds with those water molecules, and then the water molecules have lost their potential ability to move because they're bonded to the solutes like this, just weakly. It's not a permanent thing. There's a lot fewer free water molecules which are in fact able to move. So effectively, when we add solutes to water, they're having a negative effect. They're reducing the potential for the water molecules to move. We give water, pure water, a water potential of 0, and as it's a kind of pressure, we measure it in kilopascals. And then anything we've added reduces that. So let's say the squash we made had a water potential of minus 200 kilopascals. And all solutions have a negative water potential. What that means is we actually get a much simpler definition of osmosis. So if we write it out in terms of water potential, instead of having to worry about whether it is going from a dilute to a concentrated solution or an area of high water levels to low water levels, we can say instead that osmosis is the movement of water from an area of high water potential to an area of lower water potential across or through a partially permeable membrane. And then you end up with diagrams that look a bit like this. And they've shown you two, sometimes they show you 3 or 4 cells and you have to draw more than one arrow on it, but you've got to show where the water will be going. And we've just said it's going from the higher to the lower water potential, or to the more negative. So you would say the water is going to move this way because minus 200 is the higher water potential, minus 500 is the lower water potential, so that's more negative. And we can show that in the form of a diagram as well. So here's our minus 200 side, and here's our minus 500 side. And the big pink dots are the solutes, and the smaller ones are the water. So this on my key, that's the solute particles, or my squash from the example at the beginning. And these smaller ones, they're water molecules. And here's our membrane. And if we look at the membrane, we can see that the water can fit through the membrane, but these solute particles can't because they're too big. So in this particular example, the solute won't be moving. It's just going to be staying where it is. That's not always true. Sometimes solutes will be moving, but we're only really thinking about the water. And on this side, the minus 200 kilopascals, there's still quite a few free water molecules which will be able to move. Whereas on this side, there's far fewer free water molecules which are able to move. So the solute is having a negative effect on the water potential. And that means that the net movement, the overall movement, will be from the minus 200 to the minus 500. It doesn't mean no molecules will move the other way, because that's what net means. Net means overall. So this one's free, so it might go that way. But overall, more have gone to the more negative water potential. So that's how that's all working. Now we can think about the effect of these solutes in terms of a formula. And it's really easy for an animal cell. We call the effect of the solutes, this negative effect that they're having on the water potential, either the solute potential or the osmotic potential. If you're doing Edexcel biology A level, it's osmotic potential, but you might see it referred to as solute potential elsewhere. And so they are pretty much the same thing. And the water potential is being affected by the solutes. So it equals the solute potential. And for an animal cell, that's where we stop. Water potential equals solute potential. But the plant cell has a cell wall, so that also exerts a pressure. So for a plant cell, it's solute potential or osmotic potential plus that turgor pressure. And that's really important. The cell wall is exerting a pressure on the inside of the cell, preventing too much water from moving in. That's why plant cells don't burst. If you put an animal cell into a very dilute solution or pure distilled water, so much water will move into the animal cell that it will burst. If you put a plant cell into that, water will move in until the turgor pressure builds up and the cell wall is pressing on it and no more water can move in. So plant cells don't tend to burst. So we can look at that and have a look at some of the types of exam questions that we get on this. So often they give you the formula. So water potential is turgor pressure plus osmotic potential. You can write it out in these symbols. That's a psi. Psi, water potential, equals turgor pressure, P, plus pi, which is a bit weird because obviously that's the same as the pi we use in maths, the same symbol, but it's actually referring to the osmotic potential here. And in these exam questions, they give you that, and then this is the type of question you end up with. What will happen if a plant cell is placed into distilled water? So if we place our plant cell in distilled water, will more water leave than enters? Well, no, this is distilled water. That's got the highest possible water potential. Will the cells become turgid? Yes, they will, because water will be moving in, and turgid means the cell membrane is pressing right up against the cell wall. Will the tissue become flaccid? No, and we're talking about cells anyway, and flaccid is what happens when all the water's moved out. And will the cells burst? No, because it's got a cell wall. So the answer here has got to be B. Next question. When the plant tissue is in distilled water, the value of P will decrease. P is the pressure from the cell wall. That's not going to decrease if we add more water. Pi, the osmotic potential, will decrease. No, that's not going to happen either because the solutes are still there. They're still having that negative effect. P will increase, the turgor pressure will increase. Yep, that's definitely true because there's water going into the cell, so it's going to be like a really, really full balloon. And the water potential will not change. Well, the water potential could well change because we're moving water about. So it's got to be C. The pressure will increase. And then this is the final type of question you get in your exams on this. Which row of the table is correct if the value for water potential is 0 kilopascals? So water potential is turgor pressure plus osmotic potential. So they've got to add up to 0. But it can't be 0 and 0, because the cell will not have an osmotic potential of 0. It's not full of distilled water. So it can't be that one. The pressure exerted by the cell wall is always positive. It can't be negative. That doesn't make any sense. It would be pulling water in, so it can't be that one. We've got this one, pressure of 4.6, positive, great, and osmotic potential of minus 4.6. That works. And it definitely can't be this one, because 0 can't possibly equal 4.6 plus 0. That's, not how maths works. So the answer to that one is also C. I hope this has helped you understand water potential a bit more. More A-level videos coming soon, and don't forget to follow us on Instagram and TikTok as well. All the links are in the bio.